So let's talk about headphone testing. As you're probably aware, there's many kinds of headphones. And in order to measure the headphones correctly, you have to understand a little bit about the different types of headphones. You also have to understand the difference between a headphone measurement and a typical loudspeaker measurement. Similar but different. And in order to do that, you have to understand ear simulators, like we have inside here. In fact, I'll show you a little later, but you pull his pinna off. Don't rip it. It costs you a lot of money if you do. That's his ear simulator. And I'll explain it in detail. That hurts. Okay, and then let's talk about choosing the hardware and the different test methods and metrics. And then a little bit about, for example, Bluetooth headsets or headphones. And then I'll finish with a noise canceling measurement demonstration. So headphone types. So you already saw what we'd call circumaural headphones. It means they go over the ear, and if they're big enough, they should seal very nicely and have good low frequencies. Supraaural sit on top of the ear, pinna. Typically, they do not seal. There'll be a leak. And then you, of course, have earbuds, which I don't have my white ones, those iPhone ones. So those actually rest inside your pinna and definitely do not have a good seal. Mine even fall out whenever I leave them in. And then you have things like in the ear, which is quite a bit different in that they're made to go inside the ear canal and have a good seal. A lot of people don't find them comfortable, though, unfortunately. Personally, I like these a lot. Oops, okay. Over to you. Or did you? Good enough? I think everyone is familiar with the different types. So just quickly, kind of, I haven't actually gone over my measurement setup very much, but just real briefly, we have different types of hardware here. Typical loudspeaker setup, we have something we call Amp Connect, which is a USB audio interface with some signal conditioning. Nice thing about Amp Connect is I can plug a loudspeaker or headphones directly into it and a measurement microphone directly into it. And just with one USB cable, I can then go into my software and make measurements. We also have, actually I don't see it up here, we have another box called Audio Connect. Is there one? I think I forgot to pull it out of my bag. Anyhow, I can show it to you later. That is a very small all-in-one audio interface. Can you grab it? Yeah, right in that. Thanks. Thanks. Yeah, you can pull that off. So this is one of our latest pieces of hardware. What's kind of nice about this is it's portable USB. You even have headphone in and out. So you can either use the headphone to listen to the microphone signal or test the headphone. And it's stereo. So nice and portable. That's showing this setup. Now it doesn't have an amplifier like Amp Connect. So we also have, it's hooked up here. When I was powering this loudspeaker, one of these boxes is called SCAMP, and it's just a power amplifier that can also measure impedance. Both the big box and the small one can measure impedance with a internal reference resistor, which is actually patent pending because it's built into the feedback loop of the amplifier. So these are just your typical loudspeaker setups. But now for headphone testing, it's really not all that different. In fact, the only difference is you need some sort of ear coupler, head and torso simulator, stereo typically as opposed to one channel. Again, you could also even use, we don't have it here, but you could use this for just doing headphone testing because you don't need an amplifier since you're testing headphones. So now let's talk about couplers and ear simulators. So why use them? So really the biggest reason to use them is we want to simulate the human ear. And the human ear is a mechanical device and it has an acoustic load. What do I mean by an acoustic load? Well, basically, if I hold, probably the best example of this, if I don't hold this up against my ear, I actually don't hear very much sound coming out of the headphones, right? But the moment I put this over my ear, I now have a closed or a coupling between my ear and the headphones, and all of a sudden I can hear a lot of bass. So really, if I were to try to measure these like a normal loudspeaker, they would look terrible. There would be no low frequency information. So we got to simulate that. And different headphones have different acoustical impedances. This has a different acoustical impedance than an open ear headphone typically. And then of course the other thing we want to simulate is how the product is used in real life. So we have different types of couplers. We have a very simplified what's called a 2cc coupler, which was really developed mostly for hearing aid testing. Literally all it is a microphone with a cavity that is 2cc. Then we have some more fancy ear simulators. This is a very old design. It's called IEC 318. It actually is a little more complex. It has not just a, I think it's a, forget if it's 0.7. There's two volumes in here. There's actually a well-controlled, a bigger volume and then smaller volumes, which more realistically reproduce the acoustic load of a real human ear. So this one is not very realistic. This one's a little more realistic, typically used for telephones, although pretty much not used at all anymore. And then this is probably the most popular one nowadays, is the IEC 711. And here is basically what's inside hats. It's a little hard to tell because it's buried inside the head. But if you were to take this apart, you in effect find this 711 coupler, which is a standard. I highly recommend if you're doing headphone measurements, you use a 711 coupler. You can get it in different varieties of, how do I want to say, whether it's in a head and torso simulator or it can be a standalone. I think I have a picture of that, although no, I don't, unfortunately. Sometimes you see it in a little stand known as either a B&K has one called a 4153, and Grass has one with a pinna, and they call it a cheek and ear simulator. I forget the model number. So what's the difference when you measure a loudspeaker in the free field versus a headphone? Well, okay, DH handed me the two examples that I mentioned. This is a B&K 4153. Take it apart. You can see it's nothing more than a 1/2-inch microphone mounted in a 90-degree angle to a preamp. And then here is the IEC 318 that you see up here, only B&K. If you want, we can pass this around. And then over here, we have a Grass 43 something or other. I can't remember. It actually has a number on it. Again, if you take it apart, so the microphone is actually permanently mounted inside the coupler. And it's a little more, so instead of the chambers, the acoustic chambers being separate as it is in this device, It's more integrated and more representative of a real human ear than that particular one. This is exactly what's inside. If you look inside here, is mounted. The main difference is the pinna that goes on top, which is, of course, more realistic. If I can get it in. I can't do it. Okay, so let's talk about the measurement size now. So normally when we measure loudspeakers, and we're going to see this a little bit later with a Bluetooth loudspeaker and a microphone, you know, we just have a reference microphone, we have our loudspeaker, and we just place it far apart. And if it's the perfect loudspeaker, we expect it to measure flat. That's not the case when we measure headphones or earphones. So in this case, we have, for example, a loudspeaker. It could be this loudspeaker here, and it's going to be going into the microphone inside the ear simulator. We refer to that, where the microphone is, as the drum reference point. So literally think of it as the eardrum. And if we measure it, we now get this bump, kind of a squiggly line, this bump up here, somewhere around 18 dB at 3 kilohertz. And you got to ask yourself, why is that? Well, the answer is pretty straightforward, is that we have an ear canal, just like a real human ear, that has a resonance. And because we have this cavity inside, we get this bump. Again, like a real human ear, about 3 kilohertz. So if I measured a perfectly flat headphone, quote flat, I would expect to get the same response here. And a little later I'll talk about, there's a lot of debate over how this should look exactly. And it has to do with where the sound's coming from. But I'll show that later. But in effect, you don't expect headphones, when measured on a head and torso simulator or any ear simulator, to look flat. So now it's important to choose the right hardware for the application. And this really depends on both the fit of the earphone as well as cost, like and practicality. For example, development versus production, R&D versus production control, quality control. So if you want something realistic, you have a choice. You basically need a pinna, because that's going to make a big difference about how the product fits and seals at low frequencies. There's one of them, there's a simplified one, which I jokingly call a blockhead. You can't see it here, but it has exactly the same couplers as this guy does, and 2 pinnas, but it doesn't have a mouth, it doesn't have all the fancy stuff, and it's just for measuring headphones or noise cancellation headphones. So it actually simulates real use, but it's not going to be quite exactly the same as a head and torso simulator such as this or this, because depending on what you're trying to do, the body, the head, can affect the measurements. If you're measuring just headphones, no problem. But if you actually want to measure, for example, the microphone in the headphones, most headphones these days have a microphone built in for talking, then you're going to use an external loudspeaker, and you actually want these reflections in the shape of the head will have some effect on the response of the microphone in the headphones or the headset. And typically these devices, they have these correction curves, a little bit like what I think what we heard Professor Lee talking about. So this can be considered a correction curve, and there's typically 2, diffuse field and free field. I'll show you those in more detail later because, again, it's a little bit of a debate which is the right one to use. And again, if you're doing noise canceling measurements, you need to simulate the real pinnas and ear couplers, or ears, I should say. And typically you want to do several measurements because positioning matters. So you might do one measurement like that. You kind of adjust it. You take it off. You put it back on. And the reason for that is the positioning is never going to be identical, which is in real life. You saw when I measured Professor Lee's headphones, I had one channel had a better seal than the other. If I were to measure it again, I would probably try to fit it a little more tightly on that channel. So it's just like real humans. If you ever listen to these, you start adjusting it. So typically it's a good idea to do averaging. Okay, so a little more about the fixtures. So in production test, we're not trying to go for some, typically for a pinna, we're trying to go for a repeatable fit. And if we want to do limits, it better be very repeatable. So typically we use a fixture custom built for the application. It really depends on the type of headphones. Often I've actually seen like in the ear headphones where they literally have some tight fit with a custom mold essentially where this goes right in and is very repeatable every time. Well, that's pretty good. Again, not necessarily too realistic, but very repeatable. And then, of course, if we don't get a good seal, we're going to have what we call acoustic leak, which means at low frequencies, it's going to roll off. We won't have good low frequency performance. So sometimes you'll see a clamp. Most of these guys will come with a clamp if it was depending on the type of headphone to get a better seal or more repeatable. So typical things to measure, I showed you already, was frequency response. And now you got to be a little careful with when you talk about correction curves, whether you show the measurement with or without a correction curve. The measurements I showed you previously of the Stax headphones as well as Professor Lee headphones were actually using what was called a diffuse field correction. So ideally we were trying to go for a flat response because we were taking out that bump. So it's very, very important you specify that in your measurements. If someone hands me a headphone measurement without telling me how they measured it, it's useless. I need to know exactly what coupler they used and whether they applied a correction curve. Without that, I don't know what I'm looking at. Sensitivity, typically in dBSPL for a particular stimulus level. So I put 100 millivolts in, I get how many dBSPL out. I may want to take a range of frequencies. Sometimes people just specify 1 kilohertz. But it's a bit dangerous if you just specify one frequency, because what happens if you have a cancellation or a dip at that frequency? It's not going to be very representative of the overall sensitivity of the headphone. Distortion. Now, if it's R&D, typically total harmonic distortion, but if it's production, we want to know if there's any buzzing in there. Something's not, a part's loose. So we'll talk about rub and buzz, but that's typically a manufacturing problem, not a design problem. Impedance. Not a lot of people measure impedance on headphones, which is kind of a shame, because just like with loudspeakers, it tells you quite a bit about the low frequency performance of the headphones. Typically in production, it's kind of a pain because you got, instead of just 2 channels, one left acoustic, one right acoustic, you then have 2 impedance channels, left and right. So you need a 4-channel analyzer or audio interface. So you got to pay something for that. But for R&D, it's always a good idea to measure impedance. And if you want, you can even do teal small parameters. As I mentioned earlier, we look at the channel balance between left and right. If it's good imaging, it's going to be well balanced. And then there's also a standard, which I'm not going to demonstrate today. We have a sequence that we've written for doing what's called max SPO according to this EN 50322 that has to do with sound exposure levels. So if I'm listening to my headphones on my, I don't know, my MP3 player or my phone, I don't want to damage my hearing by listening too long to loud music. This tells you what is the maximum sound pressure level that you can play at for, I believe it's 8 hours. And it can just give you an indication. There's certain countries require the standard, in particular France. And if you try to sell some headphones into France that don't meet this spec, and if it fails, they're not going to let you sell them in France. Okay, a little later, Mac is going to demonstrate some Bluetooth measurements, but you can also have USB headphones, and one of the nice things about SoundCheck is you can actually measure directly Bluetooth or USB because SoundCheck is compatible with multimedia, Windows multimedia. We even have now a version of SoundCheck that will work on a Mac OS as well. So we'll come back to that. You still have the standard test methods, same metrics, but now you have to talk about a digital signal. Essentially, you're going to have some sort of digital in and out, depending on whether it's a headset or just a headphone. And then you have to define the level in dBFS. So instead of it being so many dBSPL with so many volts in, it's going to be so many dBSPL with so many dBFS in. So it's a little different, but it's also quite easy to do. Some headsets, you have to be a little careful with sign sweeps. Bluetooth is notorious for having dropouts. So we've actually, Mac will show you this in a moment, we have a calibrated Bluetooth interface with a high output power to minimize any Bluetooth dropouts due to the connection. But sometimes it's a good idea to also try things like multitone or noise as well. So just something to be careful about.